Okay, so we're going to talk about a very nice application of this whole independence and this birthday/coincidence analysis of FOCS-twins to search and hashing. And you know, there's a pretty big company whose name starts with a G that makes its living off this. This is a very important algorithm in computer science. Okay, now I took the liberty of drawing an example, a concrete example, which we can use to just sort of fix the problem. Okay, so you have 3 web pages, and of course the world has many more. It's a much more challenging problem in practice. But imagine 3 web pages. You know, page 1 has text, dirty apples hurt health. Page 2, health freaks hate dirty apples. Page 3, you know, survey, people hate bananas. Okay, so, you know, you've got some text on various web pages, and now you want to facilitate search queries. So someone might come and put in a query like apples, and you have to, you know, return the search result. You know, apples appear on page 1, web page 1 and web page 2. So you have to return the result page 1, page 2. Okay. Now, the standard way to solve this problem, and forget about what's going on at the bottom. The standard way to solve this problem might be, you know, it might be what we could call a web address directory, just like a telephone directory. Okay. Take every word, okay, and sort the words. Okay, just like a telephone directory sorts names. So sort the words, okay, and then to each word attach a list of the pages it appears. Okay, so now when you search apples, you find the word apples in your directory, apples, and you return page 1, page 2. If I search the query hate, you find the word hate in your directory, and you return the page. You return the query the search result page 2, page 3. Okay, so the algorithm here is find word in directory, okay, and return pages. Okay, we can ask, you know, how long is this going to take? So if you had n words, and there are many words, so if you have n words, okay, then you have to sort it n words, and now you need to find a word, and we can use binary search, and so we all know that takes order of log n time. So order of log n time. Search. And that's pretty good. Except that when n is big, log n might be 10, 20, who knows, something like, you know, a reasonably large number of seconds. Okay. And that's not good enough. Humans want instant gratification. So they want order of 1 search time. Okay, we've studied order analysis before, so you know what we mean by order of log n versus order of 1. Constant, instant gratification. So what about constant search time? Okay. So if you want constant search time, then basically the only data structure we really know that gives you more or less constant access to the elements is a table or an array. So now you have to use an array. Okay, and that's what I'm showing here, an array of size 11. Having indexed by 0, 1, 2, up to 10. And so if you store, instead of in a sorted list, instead of storing in a sorted vector, if you store them in a table, then you can instantly jump, for example, to, if you search for hurt, you can instantly jump to table entry 2 and figure out, you know, hurt. As long as you know that hurt is stored in table entry 2. Okay, and that's where hashing comes in. Hashing comes in to give you constant time search. Okay, but you need to first create your table, and you need to have a way of sort of remembering and being able to instantly go to the table row that contains a particular word. Okay, and so here's how hash does it. Okay, so step 1 is we say you hash the words. Hash the words to a hash table. Okay, and what does this is usually what we call a hash function. So there's a hash function that we call it h. Okay, and this hash function takes as input a word. So it's a function. So it takes as input a word and tells you what table will you store the word. Okay, so for example, and the typical types of hash functions are built in the following way. So the hash function, for example, of hate. Okay, so now we need to find a number between 0 and 10 for hate. Okay, so now each letter is given a number. For example, h equals 8, a equals 1, and so on. Okay, so you take each number corresponding to the letter. So in this case, you have the numbers 8, 1, 20 for T, and 5 for E. Okay, and you raise it to some large power, like a large prime power, for example, 17. add them all together. Okay, but now since you want a number between 0 and 1, you take the remainder modulo 11. So you take the remainder modulo 11. Okay? And this will give me the value 7. And so you see that hate is stored in table row 7. Okay, so you can instead of storing your words in a sorted list, what you do is you take each word, apply your hash function, and it tells you the table row. Now if you want to search, some query, for example, you want to search hurt. Okay. Well, you first compute the hash function of hurt. You compute hash of hurt, which gives you 2, and that tells you the table row that hurt is stored in. And the nice thing is that this hash function is quick to compute. It's a constant time computation. That's important. Okay. So that takes you to table row 2, and you immediately find hurt, and you return the search result P1, and it's all taking constant time. Okay. Now there's a problem. If you wanted to search hate, so you first hash hate, okay, and that takes you to table row 7. So you go to table row 7, and anyone see the problem? The problem is what you find in table row 7 is not hate, but you find freaks. Actually, the problem is not that you find freaks. The problem is that there are more than 2 words, there are more than 1 word that are stored in table row 7, freaks and hate. So actually what you have to do is you have to come to table row 7, and then if you don't find, you have to find hate here. Okay, so, or it's nowhere. Okay, so you find freaks, you say, oh, that's not hate. So now you go to the next one. Oh, that's hate. Okay, and now that you found hate, you can return the search result page 1, page 2. Okay? But that's now taking more time, a little more time, but even a little more time is bad. So this is an example of what we call a collision. Okay? So when you search for hate, you see there's a collision. So 2 or more words are stored in the same table row. Or more words in same row. I mean, it's not a disaster. So then what that means is that you have to search the row. If you don't find it in your first attempt, you go to the next one and the next one. And so you might have to search everything that's stored in table row 7. Okay. But as long as there are no collisions, then you don't have to worry about that. If there are no collisions, okay, then when you go and search for hate, and if it takes you to, row 7 and there's nothing there, it means that no web page has the word hate. On the other hand, if it's in some web page, it'll be in 7. So ideally, we want no collisions. So let's see how we accomplish that. So we want no collisions. And how to accomplish that. So that's what we're going to talk about. But let's have a little bit of a preamble to that discussion. The first is, well, what is this hash function h? Okay. So that's a business. There are people who are spending their entire, research, on constructing good hash functions. Okay. Now, what is a good hash function? A good hash function, well, first, it must be quick to compute. So you want to be able to compute it in constant time for words of a certain fixed length or shorter. Okay. So it has to be quick to compute. Okay? Because otherwise it's going to take you too long when you want to search for hurt, to hash it and find out where it is. Okay? And the other thing is that a good hash function more or less takes words and randomly distributes them among table rows. Randomly, independently. In other words, 2 words that might have, so for example, hurt and hate. They're very similar words, but look, they've gone to way different, table rows. 2 versus 7. And that's indicative of the fact that you can think of this as, hurt is picks a row kind of, at random, and hate picks a row at random independently. So those are the qualities of good hash functions, and we're going to take that for granted. It's someone else's business to give us a good hash function. Okay? So that's fixed in an application. You take some standard hash function and you assume it's a good hash function that has those 2 properties. It's quick to compute and independently and randomly distributes the words, with equal probability to go into any particular row. Okay? So we don't have control of the hash function. We take a standard hash function. What do we have control over? Well, what we have control over is the number of bins. Okay? Because you can clearly see that if I have more and more and more and more bins, then it's less and less likely that you're going to get a collision. Okay? So let's see how to choose the number of bins. Okay? And that's where the FOCS-twin analysis is going to help us. Okay, so let's compare, hashing with the FOCS-twins scenario. So hashing and FOCS-twins. Okay, so now in hashing you have words, W1, W2 up to Wn, okay, and we're going to hash these into a table. Okay, and in the FOCS-twins scenario, we have students S1, S2 up to Sn, and they have birthdays. Okay, now where do we hash? We hash into a table with bins 0, 1, 2 up to 10. Well, in general, 0, 1, 2 up to b minus 1. So bins 0, or table rows, so you hash into table rows 0, 1, 2 up to b minus 1. Okay. And in the FOCS-twins scenario, we are hashing, students are born on days, birthdays born on days 0, 1, 2 up to b minus 1. Okay, so you have b birthdays. Okay. We started them before at 1, but we can start them at 0 and then go up to b minus 1. Okay. And now in the situation of FOCS-twins, we were looking for FOCS-twins. We were interested in the probability of FOCS-twins. Okay. So we had FOCS-twins. So FOCS-twins are, we're interested in the situation of no FOCS-twins. Okay. And that's what this formula gave us, the probability of no FOCS-twins. Okay, if you considered student 1, 2, 3, and so on up to k. Okay. And here, we're interested in the situation where you don't hash into the same row, no collisions. We can call those hash twins. We're interested in no hash twins. Okay. And the scenario is exactly the same. People are born on random days with equal probability. If the hash function is good, it hashes a word randomly into one of the bins. The same number of analogous situation. Birthdays correspond to rows. Okay, and if the hash function is good, it hashes words independently, and we assume that birthdays are independent. So the setup is exactly the same, where words correspond to student and rows correspond to bins. Okay, and so the probability of no hash twins, the probability of no hash twins, i.e., the probability of no collisions, is exactly equal to, now this is the birthday problem, right? Because we're going to ask none of the words. We want all the words to not have a collision. So we go from, we start with b possible birthdays, b possible rows. So it's b minus 1 over b times b minus 2 over b times b minus 3 over b times, and so on, all the way up to n, b minus n plus 1 over b, okay, times when n equals k, so this term is 1. So the probability of no collisions directly using this formula is exactly this value. Okay. And we want no collisions, so you should choose b enough such that this b large enough, it turns out b large enough such that this probability is large, so that the probability of no collisions is large. Okay, and that happens when b is large. So let's take an example. Supposing you have 10 words. Okay, so n equals 10. Okay, and now let's look at the probability of no collision, so that search will be super efficient. Let's look at the probability of no collision for different table sizes. Okay, so different table sizes. So table size b, and we'll try 10. Okay, so this is equal to n. We'll try 20. This is equal to 2n, and we'll keep going. 30, 40, 50, then we'll go up to 100, then we'll go up to 500, then we'll go up to 1,000. Okay. Various table sizes. Okay. And we're interested in the probability chances of no collision. Okay. And it turns out, so let's see what's the calculation for n equals 10. For n equals 10, what we're going to have is b minus, when b is 10, so we're going to have 9 over 10 times 8 over 10 times 7 over 10 times ... Okay, 1 over 10. Okay. This number is approximately equal to 0.0004. Okay. So the chances of no collision, the chances of no FOCS-twin, the chances of no collision is basically 0.0004. Okay. It's overwhelmingly likely that you will have a collision, at least one collision. And we're being very strict. We want no collisions so that no matter what you search for, it's going to be very efficient. Okay. What about if n equals 20? Now, if n equals 20, this number goes up significantly, 0.07. So there's a 7% chance that when you hash, there'll be no collisions. What about n equals 30? It goes up a lot, goes up to 18%. Okay. N equals 40, it goes up a lot to 29%. See how it's going up rapidly as you increase the table size? When n equals 50, it goes up to 38%. Okay. N equals 100, we're at 63%. N equals 500, we're at 91%. And n equals 1,000, we're at 96%. So even with 1,000 rows in your table, okay, it's still the case that there's a 4% chance of some collision. But we want 0 collisions. That's quite strict. Okay. Theorem. Okay. If B is in little omega, remember little omega, growing larger than, if B is in little omega of n squared, so if the table size is slightly larger, rising slightly larger than n squared, then the probability of no collisions goes to 1. So you will have no collisions. That's quite strict. Okay, now this represents a very standard trade-off in computer science, okay, where, what we're after is kind of instant search. And the price we pay for that is a larger table size, n squared. Okay? So as n gets larger and larger, n squared suffices, okay, to give us no collisions with overwhelmingly large probability, close to 1. Okay? So if you give me more memory, I can get you much faster running time. And that's a standard trade-off in computer science. And we see it here with hashing. Now, of course, this can be a very large memory if n is, let's say, 1,000,000 words that you want to hash. Okay, so this may be unbearable. So what you do, you allow some collisions, and you can do this analysis asking what's the probability of at most 5 collisions, at most 10 collisions. So at most 5 or at most 10 collisions, means that when you get to a table row, you'll have to search at most 10. Okay, that's still a constant. Okay, so you still get nearly instant search. Okay, so that's the application of the birthday paradox and this analysis of independence and coincidence. Okay, to hashing. It shows that you can get very efficient search, good hashing if you have large table size and avoid collisions. Avoiding collisions is exactly the birthday problem. So let's erase. We're going to come back and talk about random walks.